Hi, welcome to Introduction to Understanding Measurement Uncertainties, a series for teachers and students. Hi, and welcome to the channel Think Like a Physicist. This is an introductory video to the playlist Understanding Measurement Uncertainties, a series for teachers and students. This playlist has two main goals. The first goal is to explain why measurement uncertainties are critically important in science. As part of the scientific method, we test hypotheses by performing measurements. But all measurements have uncertainties, and we must understand these uncertainties to conclude whether the result of a measurement agrees or disagrees with the hypothesis we wish to test. The second goal of this playlist is to give a better understanding of what a quoted measurement uncertainty actually means. For example, if the distance to a star is measured to be 2,000 plus or minus 100 light years, what exactly does that tell us about the true value of that distance? Does it mean that the distance is between 1,900 and 2,100 light years? In short, no. In addition, we hope that the content of this playlist will also make it easier to understand that science isn't static and understand how new hypotheses replace old ones, understand new scientific findings in context with old ones, and apply the same knowledge in contexts outside of science. To roughly illustrate why understanding measurement uncertainties is important to the progress of science, let's talk a little bit about what science does. Science is the practice of accumulating information about the universe by forming and testing hypotheses. Or, put another way, science is how we figure out what reality is. We observe natural phenomena and come up with hypotheses which possibly explain those phenomena. We then devise ways to experimentally test those hypotheses and perform those experimental tests. If a hypothesis's predictions agree with the results of the experiments, we keep it around. But if they don't, then we need a new hypothesis. Then we make more observations of natural phenomena, and so on. Now, this roughly describes the scientific method, but it glosses over some important details. To see one issue with this description, let's ask a basic question. How do we prove a hypothesis false? This question may seem silly at first. After all, if the hypothesis makes a prediction and observation disagrees with that prediction, haven't we disproven the hypothesis? But experiments aren't perfect. If we measure some quantity, that measurement has an uncertainty. So scientific progress requires us to make judgments on the validity of hypotheses using measurements which have uncertainties. This means that we don't just say that a hypothesis is false. Instead, we have to quantify how much that hypothesis disagrees with observation. When disagreement between a hypothesis's prediction and the result of experiment is sufficiently high, we stop taking that hypothesis seriously as a true description of nature. So, as science progresses, we don't just make an increasingly longer list of things that we know. We also have to quantify how certain we are of the things we know. Measurement uncertainties are thus important for understanding how science progresses. For example, let's say you have two competing hypotheses to explain some natural phenomenon. Both hypotheses have passed all experimental tests to date. Let's say they predict slightly different values for some parameter p, which you can measure experimentally. So you measure p and get some value. If the measurement uncertainty on p is larger than the difference between the two hypotheses' predictions, your experiment can't meaningfully favor one over the other. But if your measurement uncertainty on p is small compared to the difference between the predictions, you can experimentally rule out one in favor of the other. And of course, if your uncertainty is much smaller than the difference between the measured value of p and either prediction, you might rule out both hypotheses. So, over time, as experiments become more precise, some hypotheses which previously agreed with all observations will fall by the wayside. And even if you have a hypothesis that has passed all experimental tests so far, it's important to know just how well it has been tested so that you can have some idea of how it could fail in future tests. Okay, so this playlist consists of 7 videos after this introduction, which can be divided into 2 groups. First, we have 3 videos explaining the importance of measurement uncertainties. These are Science as an Iterative Approximation to Nature, All Measurements Have Uncertainties, and Why Measurement Uncertainties Are Important. Then we switch to a discussion of how error bars are defined, what they tell us, and what they don't. In particular, we discuss something called Gaussian error bars. Gaussian error bars are not the only way to quote a measurement uncertainty, and for some measurements, they're not even appropriate, because they're not even correct. But they are approximately correct for a wide range of measurements, and they are one of the most common ways of quoting an uncertainty. So, if you see a scientific result saying that the distance to a star is measured to be 2,000 plus or minus 100 light years, it's very likely that the plus or minus 100 light years is a Gaussian error bar. We thus have 4 videos discussing Gaussian error bars: Qualitative Description of the Random Walk, Random Walk with a Varying Step Size, Qualitative Discussion, Introduction to Gaussian Error Bars, and How to Interpret a Scientific Measurement with Gaussian Error Bars. Now, we will leave some mathematical details out of these videos and focus on a qualitative discussion of the ideas presented here. We'll give pointers to other videos on this channel where mathematical derivations and additional information can be found. We will mention one helpful hint about this channel. The videos are color-coded depending on their overall theme. Introductory videos like this one have a light blue background. Videos about probability and statistics have a purple background. Videos focused on science and scientific methods have a salmon-colored background. And finally, videos about real-world examples are given in green. Now, this playlist is a work in progress and may be updated with new videos as time goes on. Feel free to leave questions in the comments section below each video. Comments on how these videos could be improved are much appreciated. If anything is unclear, if more background information is needed, or if there is anything else that could make these videos more useful, please let us know. Okay, so there is a link to the next video in the playlist, Science as an Iterative Approximation to Nature, in the upper right-hand corner of the screen. If you'd like to know when new videos on this channel are released, please hit the subscribe button.